Thanks everyone for coming to my defense. Today I'll be presenting my thesis on documenting the evolution of a Southern California coastal lagoon during the mid to late Holocene. Before we get started, I just want to acknowledge the indigenous Kumeyaay population on whose ancestral land my fieldwork was conducted. San Diego remains unceded Kumeyaay territory. So here's an outline of what I'm going to be talking about today. First, I will explain some background information about coastal wetlands, Ostrea lurida, which is an oyster species important to the study, and our study site, Los Peñasquitos Lagoon. Next, I will go over the methods and the results, and then we will get into the discussion to explain our sedimentary facies and shell interpretations, reconstruct the paleoenvironmental history of the lagoon, and lastly, go over the implications for restoration and conservation illuminated by this study. So let's start with some background information. All right, so what exactly are coastal wetlands? They are a wide variety of complex ecosystems found in and around coasts. Some examples of coastal wetlands are estuaries, lagoons, coastal plains, deltas, tidal flats, and marshes. They exist on all 7 continents, in high and low latitudes, and at active and passive margins. On this map, we can see that the type of coastal wetland that forms can be influenced by climate. So mangroves are common in warmer climates near the equator, and temperate and subpolar regions more often have marshes. Other factors that impact wetland formation are antecedent geology, which just means the geomorphology of the existing area, or in other words, the type of bedrock and the physical shape of the land, tidal forces and sea level, and sediment influx from a river system. When tidal forces are stronger than river discharge, estuarine systems form. This includes wetlands like estuaries, lagoons, and marshes. And an estuarine system is essentially a body of water that is adjacent to the ocean. When sediment influx is stronger, you get prograding deltaic systems like this delta in Alaska. Deltas have a branching structure where you can see the river or fluvial sediment building out into the ocean. However, coastal wetlands do exist on a complex continuum. Deltas and estuaries are not mutually exclusive, and there are multiple paths of progression between these highly interconnected environments. For the purpose of this study, we focus on estuarine systems, which are far more common on the Pacific coast. So 3 wetlands that are most important to the study are estuaries, lagoons, and salt marshes. And now I'll provide a quick overview of each one. So what is an estuary? It is a semi-enclosed coastal body of water where saltwater and freshwater mix. There are a few different types of estuaries. The most common is river flooded valleys, but there are also bar-built, tectonic estuaries, and fjords. All estuaries are formed when an area of lower elevation adjacent to the coast floods as sea level rises. The most modern estuaries formed when sea level rise stabilized following the last ice age at the beginning of the Holocene about 11,000 years ago. What is a lagoon? A lagoon is an area of shallow water that has been partially cut off from the sea by a barrier. The primary difference between a lagoon and an estuary is that the barrier heavily restricts tidal flow, while an estuary can be more open to the tides. Lagoons also do not always have a river or fluvial source, whereas estuaries do. Lagoons form when a sandy or coral or reef barrier is formed across the mouth of an estuary or embayment. They can be ephemeral features, which just means that if the sand barrier is flushed out, it can revert back to a higher energy estuary. Alternatively, if the barrier migrates and blocks the tidal channel, a lagoon can infill with sediment and become a marsh. Lastly, what is a salt marsh? So a salt marsh is a vegetated plain adjacent to the coast that is regularly flooded with salt water brought in by the tides. The soil is often peaty and very muddy. Salt marshes form when a coastal lagoon or estuary is infilled with sediment. They're sustained when accumulation of sediment is greater than or equal to the rate of land subsidence and in balance with sea level rise. I say in balance because salt marshes are somewhat flexible ecosystems that can actually withstand some amount of sea level rise or alternatively increased sediment accretion. They often go through phases of expansion and retreat. During expansion, a positive feedback loop can be established in which sediment is deposited, allowing for vegetation to take root and then aids in further sediment accretion. These different types of coastal wetlands are all highly interconnected. For example, salt marshes and lagoons can exist within estuary systems, and they can also transition into one another over time. Coastal wetlands are important because they provide a variety of ecosystem services that benefit humans and animals alike. Some of the things coastal wetlands provide are shoreline protection and sediment caching to prevent excessive erosion and preserve natural beaches, natural water quality management and nutrient cycling by filtering sediments. They are biodiversity hotspots and habitats for migratory birds, and they're also carbon sinks. Coastal wetlands actually account for up to 50% of the carbon transfer from ocean to sediments. And lastly, they are our natural record of geological and climate history. Wetlands have also become essential for humans. 70% of the global population lives within a coastal area, and 50% of United States populations live within 50 miles of the coast. Coastal wetlands can also, coastal wetlands can also be a source of recreation. They are important fisheries too. Unfortunately, many of our coastal wetlands are presently at risk. Modern development threatens coastal wetlands by directly building over them, utilizing wetlands for agricultural purposes without considering the potential for permanent changes to soil, damming and dredging, and even sediment supply disruption from upland development. Notably, since the industrial era, we also see climate change pose an increasing threat to coastal wetlands. This graph shows the global temperature average since 1860. Over the last century, as industrial technology has boomed, we see that the global surface temperature has increased by over 1 degree Celsius. This might not seem significant, but it has already caused polar glaciers and ice sheets, and ice sheets to melt, which will ultimately result in sea level rise. In Southern California, the threat of climate change is exacerbated by phenomena such as coastal squeeze and fragmentation. The Pacific coast is already far more narrow than the Atlantic coast because it sits at an active tectonic margin. Coastal squeeze is then when urban development pushes up against the coast, minimizing the space these wetlands have to migrate landward as sea level rises. Fragmentation is when a continuous habitat is broken apart into smaller segments, like what we see here in this photo of the Ballona wetlands. Continued development can cause the fragments to grow smaller and farther apart from one another. We see this in this photo with the channel that cuts through the center of the wetlands, the roads, and that further fragment those two portions of the wetlands, as well as the development that has been built over what was once a much larger marsh. Fragmentation and coastal squeeze disrupt the natural processes that maintain these environments, as well as significantly inhibiting the ecosystem services they provide. These developments also have a negative impact on habitats that are essential to the survival of animal and plant species, some of which may be at risk of extinction. One example of this is Ostrea lurida, commonly known as the Olympia oyster. It is native only to the Pacific coast and is a keystone species, which means that it provides services that are essential to the health of its native ecosystem. In this case, they're reef builders and filter feeders. Their historic range extended from Sitka, Alaska to Baja California del Sur. At present day, the Olympia oyster is only found between British Columbia and northern Baja California, and even within that range, the population has dwindled. Previous research has found that Ostrea lurida shells at our study site, that there are Ostrea lurida shells at our study site, Los Peñasquitos Lagoon. So here's a map showing Los Peñasquitos Lagoon. It is located in San Diego County, adjacent to the Torrey Pines State Reserve and the Torrey Pines Golf Course. It's bordered to the west by the Pacific Ocean and to the east by Freeway I-5. This map also shows our core sites, which I will speak about in more depth soon. And like all coastal wetlands, over time, the ecosystem of Los Peñasquitos Lagoon has been affected by geologic, biologic, climatological, and anthropogenic forces. Here we see a timeline depicting the history of such processes that have affected Los Peñasquitos Lagoon. The lower part of the figure shows the history of the lagoon over the last 6,000 years, while the upper region zooms in on just the past 400 years. The blue bars represent geological history, the green bars biological, the orange climatological, and the gray anthropogenic. However, it is important to note that all of these processes are interconnected and influence one another. We can separate the climatic history of the local region into two phases: an overall wetter climate, which prevailed until about 3,000 years ago, and an overall drier climate that persists to present day. Within these two phases, there have also been anomalous intervals of distinctly wetter climatic conditions, indicated by the dark orange bars. During the overall dry period, these intervals culminate with the Little Ice Age, which took place from 600 to 150 years ago, followed by the transition into today's modern arid climate. There have been three biological shifts that generally line up with those changes in climate. Mangrove and pondweed dominated the lagoon up through about 3,000 years ago, at which point grass became more abundant. This transition coincides directly with the shift from a wetter to drier climate. The final biological shift occurred with the propagation of erodium and eucalyptus pollen about 200 years ago, roughly at the same time as the shift to today's arid climate. More critically, eucalyptus and erodium are non-native plants in Southern California and are often seen as indicators of European settlement, indicated by green and gray striped bars. Prior to European colonization, the area had been home to the Kumeyaay indigenous population. In 1769, Spanish missionaries established California's first permanent European settlement in San Diego, which loosely coincides with the arrival of erodium in the region. Three notable urban developments in the lagoon in more recent times were the construction of a road across the tidal channel in 1909, the construction of a railroad through the center of the marsh in 1925, and the development of Highway I-5 across the creek entrances in 1970s. Lastly, from a geological standpoint, the lagoon has experienced four different phases over the past about 6,000 years, each of which closely follows a climatological, biological, or anthropogenic shift. Prior to 6,000 years ago, the surrounding coastal region was characterized by rocky, cobbly beaches that formed falling post-glacial sea level rise. Local sea level rise slowed about 5,500 years ago, allowing the open embayments and lagoons in the San Diego County region to start infilling and developing sandy beaches. Then, around 2,750 years ago, the lagoon transitioned to a salt marsh environment that more closely resembles what we see today. This initial salt marsh originated following the shift to an overall drier climate and subsequent floral transition to grass, and persisted until about 150 years ago. At this point, there was a local expansion of the nearshore mudflats caused by urban development, and followed by a salt marsh resurgence over the last 50 or so years. With all this context in mind, what were the goals of this study? So previous studies have not really explored the presence of Ostrea lurida and other shells deposited in the lagoon's history. So given that this species once existed here and we see their presence declining throughout the Pacific coast, an investigation into this lagoon's history could provide key insight that may aid in the conservation and restoration of Olympia oysters and Southern California coastal wetlands alike. So let's get into the methods. How did we accomplish this? To answer our question, we collected 3 sediment cores from the lagoon via the vibrocore method. Additional cores were extracted, but they were either too short or the drive was too messy for them to be usable. As a quick refresher, our core locations are as follows. Core 7 came from further inland, while cores 3 and 4 were closer to the tidal channel. We decided that core 7 would be our high resolution master core, which basically means that it was sampled at a higher frequency and its data was used as a reference point against which to compare the other cores. Once we brought the cores back to the lab, they were split open and sampled for grain size and loss on ignition. Grain size is commonly used as an indicator of depositional environment. The size of sediment can aid in characterizing the transport processes. In general, finer grains means lower energy environments, and coarser grains means higher energy environments. Because it was our master core, core 7 was sampled every centimeter, while cores 3 and 4 were sampled every 2 to 4 centimeters. Each sample was then pre-treated to remove organic matter, carbonate, and biogenic silica. Then they were run through the Malvern Master Sizer 2000, which measures the average size distribution for each sample. Calibration standards were run twice before each batch, once every 10 samples and once at the end of a session. Next, the cores were sampled for loss on ignition. The purpose of this analysis is to further aid in characterizing the depositional environment by calculating the total organic matter and carbonate material in sediments. Cores 7 and 4 were sampled every centimeter. This analysis was not performed on core 3. As a pre-treatment, the samples were weighed wet and then dried at 60 degrees Celsius overnight. After drying, they were weighed again. Each sample was then combusted at 550 degrees Celsius in a muffle furnace to burn away any organic matter. The samples were weighed again and then returned to the furnace to be combusted at 950 degrees Celsius for 2 hours to burn away the carbonate material. They were weighed one final time following this combustion. In addition to the sedimentary analyses, a shell hash layer found in core 7 was investigated to determine whether the shells were deposited in place. The core was photographed, and then the shells were extracted and identified at a species level. The shells were also examined for physical conditions such as abrasion, breakage, or color loss. This is called the taphonomic assessment. Taphonomy is the study of how organisms decay and become fossilized or preserved. And this kind of assessment can provide additional insight into the depositional environment of the shell hash layer. For example, if the shells are more damaged, that means they likely traveled a further distance or were in a higher energy environment. Lastly, a subset of shells, as well as some plant material from elsewhere in the core, were radiocarbon dated. I was fortunate enough to be able to visit UCI's Keck lab to process some of these samples myself, but the process is pretty lengthy, so I'm not going to go into it in depth here. After receiving the results, though, the radiocarbonates were calibrated using an online tool called Calib, and the shell samples were corrected for marine reservoir effect with a delta R of -43. All right, so now to get into the results. As a reminder, Core 7 is our high resolution master core, which basically means that we use it to define our stratigraphic units and then reference the other 2 cores against its data. The grain size results initially came in 10 size bins, which we consolidated down to 3 in order to plot the results on a ternary diagram. Our final grain size bins were mud, which ranges from 0 to 62 microns, fine sand, which ranges from 63 to 249 microns, and medium and coarse sand, which we're going to refer to here on out as just coarse sand, which ranges from 250 to 2,000 microns. We found that our points clustered in 4 areas, which then became our 4 units. The shell hash layer actually ended up in unit 2, shown here with the open squares, but the surrounding sediment is unit 1, so we consider it to just be a unique deposit within unit 1. So to bring that into context, we created a stratigraphic column for core 7. I just want to start by orienting you to this type of figure, which will be shown for each core. So this figure shows the core photo, with the surface of the core being the top of the figure. The photo is followed by the distribution of mud, fine sand, and coarse sand, the percentage of total organic matter, and lastly, the stratigraphic column that breaks the core into the 4 different units as determined by the ternary diagram, and also with radiocarbon dates. In the strat column, blue represents unit 1, yellow is unit 2, brown is unit 3, and green is unit 4. Looking at the strat column next to the grain distribution profiles and total organic matter, we can see some distinct differences between each one. So the key characteristics of unit 1 are that it is dominated by fine sand, the grain size is generally balanced and consistent throughout, and the total organic matter is mostly less than 5%, and as well as the shell hash layer is present near the top of this unit. Unit 2 is defined by mainly fine and coarse sand, but has fluctuating grain size balance between coarse sand, fine sand, and mud. The percentage of total organic matter remains less than 10%. Unit 3 marks a shift to finer grain sediments, as it is primarily composed of fine sand and mud. Trace amounts of coarse sand and a general fining upward trend. The total organic matter increases slightly again to be approximately 10% throughout the unit. Lastly, Unit 4 is marked by a significant amount of mud-sized grains. There's minimal fine and coarse sand, and the amount of total organic matter exceeds 10%, increasing sharply near the surface of the core. Our strategy for dating this core was primarily to identify the age of the shell layer, but we also had 2 dates determined from pieces of plant material to bracket the shell layer, the oldest being in the middle of Unit 1, an age of about 3,605 years ago, and an upper date near the base of Unit 2 at 1,100 years ago. All of the shell dates ranged within 1,700 to 1,000 years ago. It's important to note, though, that even though the strategy for radiocarbon dates was focused on the shell layer, all of these dates help us correlate the 3 cores with each other, as well as fit them within the established history of the area. So next, we plotted the grain size samples from cores 3 and 4 on the same ternary plot. All samples here clustered in units 1, 3, and 4. Here's the full core data for core 3. We see the results of core 3 in a similar orientation to core 7, but what I really want to focus on is the stratigraphic column there on the right. The progression is a little different from core 7, but still follows a finding upward trend. We start with a unit 1, followed by some short alternations between units 3 and 4. Then there's a large stretch of unit 4 and a return to unit 3 at the top. What's noticeably absent is unit 2 and the shell layer. We have one date for core 3, and it is plant material from unit 1 dated about 2,500 years ago. Lastly, we have a stratigraphic column for core 4. This strat column is very similar to core 3, where we have a progression from unit 1 to unit 3, and then unit 4. And then, as with core 3, another return to unit 3 at the top. Like with core 3, and unit 2 and the shell hash layer are also absent from this core. We have two dates for core 4, a shell from unit 1, dated at 3,760 years ago, and a piece of plant material in the first unit 3 segment, dated at 830 years ago. This is the only unit 3 date that we have, actually. So to reiterate, the purpose of acquiring dates in our master core was to identify the age of the shell hash layer. And now we're going to take a closer look at the shells we identified. So the shells that we found were Ostrea lurida, Tigellus californiensis, Argopecten ventricosus, Macoma nazuda, Cerathidiopsis californica, and lastly, Chione unditella. All of these species are native to brackish or marine environments along the west coast, and most shells showed some abrasion and moderate to significant loss of color and luster. This table shows the number of shells that were identified by species, and the main thing that I want to know about these shell counts is the number of whole versus fragmented shells. There are about twice as many shell fragments as whole shells. This could be in part due to our coring and core splitting process, but could also be the result of breakage during reworking prior to burial. So this is a close-up now of the core photo looking specifically at the shell hash layer. We can divide it into 3 segments. Section 1, where the Olympia oysters are. Section 2, which is mainly matrix sediment with only a few shells. And Section 3, which contains the bulk of the shells. In addition to breakage, we also looked at the orientation of the shells. All visible shells were either oriented concordantly, which means that they're either parallel or subparallel to the bedding surface, or obliquely, which means they're at an intermediate angle to the bedding surface. Some of the shells in section 3 also exhibited some loose stacking in a concave downward direction. And again, most shells experienced some abrasion and a significant loss of color or luster. So how do we interpret these results? First, I'm going to go through our interpretations for each sedimentary unit. As established in the results, Unit 1 is dominated by fine sand. This would indicate moderate depositional energy. Low total organic matter indicates little to no vegetation, and the presence of the shell hash layer in this unit indicates this environment likely supported those shell species. The shells identified all thrive in marine or brackish environments and cannot survive in an environment with depositional energy that is too high. With all of this established, we interpret this environment as an open embayment. Here we see an example from Hawaii, as there really aren't any comparable analogs along the California coast. You'll notice that this embayment, that it is prominently open to wave and tidal energy, which allows for unrestricted tidal exchange and limited sheltering from the full force of ocean waves. So these waves can propagate into the embayment, which is why we see sandy deposits. Next, we have Unit 2. The influx of coarser sand indicates a higher depositional environment than Unit 1. The persistently low amount of total organic matter means that there's still little to no vegetation present. This unit is also not a system-wide change, as it only occurs in core 7, which indicates that the source of the coarser sediment is proximal to core 7 or further landward. So as a refresher, core 7 is here, and cores 3 and 4 were extracted here. Core 7 is closer to the creek channels that flow into the lagoon, providing a source of sediment and fresh water. It is for these reasons that we interpret Unit 2 to be a fluvial delta. This photo shows an example of what is called a bay head delta. This is a type of delta that forms within an estuarine system at the mouth of the freshwater source. In this context, the fluctuating grain size balance indicates proximity or distance from an active channel. We would expect to see coarse sand in an active channel because the flowing water is capable of transporting larger grains. The channels can migrate over time depending on the strength and consistency of stream flow. Water always seeks the path of least resistance. A fluvial delta may also prograde or retreat as the sediment supply changes. Next, we have Unit 3. The transition to fine sand and mud-dominated sediments indicates lower depositional energy than the previous two units. We see trace amounts of coarse sand as the unit finds upward. The total organic matter is greater here than in Units 1 and 2, which means we're seeing a bit more vegetation. Given that this unit is also present at the top of cores 3 and 4, we can say with certainty that it represents an immature marsh environment. Our cores were taken from the muddy area shown in this photo. We call this Facis an immature marsh because the vegetation is not well developed. The soil is muddy, but it is not peaty or spongy because not enough vegetation has decomposed. Lastly, Unit 4 is the natural continuation of Unit 3, even finer grains dominated by mud. The total organic matter exceeds 10% and increases sharply near the surface, which means we have a lot more vegetation. We also see this unit at the top of core 7, and so can confidently interpret it to be a mature marsh. So mature just means that the vegetation is more developed, and we can see that clearly in this comparison between the two core sites. The soil at the Unit 4 area is also spongy and peaty due to the decomposition of years of vegetation. We can also see some mature marsh area in this photo of the site for cores 3 and 4, the grassy spot in the background. It looks really different from the mature marsh that we see at the site for core 7 on the right due to the influence of salt water from the tides. So given its proximity to the creek channels, our site for core 7 is actually more of a freshwater marsh. Which kind of just goes to show that even today, we see a few very different environments represented within just this one system. So we have established that Unit 1 is an open embayment, and this is further supported by the presence of the shell hash layer and the single shell found in core 4. All of the shells we identified are native to shallow marine or brackish estuarine environments and cannot thrive in areas with sedimentation that is too heavy or water that is too fresh. Our primary goals in analyzing these shells was to determine if the shells fit into our overall Facies interpretation and how they can provide further insight into the depositional sequence of the lagoon. In this analysis, we will be looking at 3 factors. First, the physical condition of the shells. Next, the sedimentology of the matrix sediment surrounding the shells. And last, the greater spatial geometry of the shell deposit within the lagoon. So to reiterate from the results, 2/3 of the shells were broken and many other unidentifiable fragments were present. However, some amount of breakage could have been caused by the coring and core splitting process, so we can't really rely on this aspect of the physical condition alone. Other whole shells and fragments alike showed minimal abrasion. Abrasion is also an indicator of transport distance. Highly abraded shells have likely tumbled along in a high energy environment before they were buried, wearing down the ridges and edges. Less abraded shells would not have traveled very far or would have been buried in a low energy environment. All shells showed significant loss of color or luster. As another quick reminder from the results, most shells were oriented concordantly or obliquely. If the shells were buried in a place where they died or in situ, we would expect them to be largely concordant with stacking or nesting as well. So what we see here is some kind of middle ground. Per the taphonomic grading system of Brandt, significant breakage would indicate intense transport and reworking, but light abrasion and oblique orientation suggest minimal transport and rapid burial. Given that a fair amount of breakage could have occurred during the coring process, we value abrasion orientation more. We also looked at another more qualitative grading scheme by Flessa that focuses on individual shells rather than the whole assemblage. With this scheme, most of our shells fit grades 1 or 2, excellent to good preservation with only a slight degree of alteration. These taphonomic grades are associated with either a short transport distance or rapid burial. So next we looked at the matrix surrounding the sediment, surrounding the shells. So the shell hash layer is near the top of Unit 1, which we interpret to be an open embayment. However, the grain size samples surrounding the bulk of the shell hash layer fall within the boundaries for Unit 2 on our ternary plot, which represents a fluvial delta. Keeping our taphonomic assessment in mind, we believe that the shells were established locally near the site for core 7 during the open embayment regime, but may have been reworked as the creek channels prograded out into the estuary and established the delta. So lastly, we look at the spatial geometry of the shell deposit within the lagoon. The shell hash layer was found only in core 7, though we did find one shell in core 4. This limits our ability to establish a greater scope for the shell assemblage, but we do think it's notable that the shell hash layer is not present near the mouth of the estuary. We believe that this further supports the interpretation that the shell deposit was reworked locally as the creek channels prograded out into the estuary during the early formation of the delta. So let's put all of this into context now to reconstruct the history of the lagoon. So this is the same timeline that was shown before, but now we've added this new bar that shows our facies interpretations. The colors of the new bar follow the same scheme, same key used for our stratigraphic columns. Blue is for open embayment, yellow is for fluvial delta, brown is for the immature marsh, and green is for the mature marsh. Throughout this paleoenvironmental reconstruction, you will also sometimes see a colored bar along the bottom beneath the dates that will help you stay oriented as we go through time. So previous work has established that Los Peñasquitos Lagoon formed as the last ice age ended and sea level rise flooded river mouths up and down the Pacific coast. It is estimated that post-glacial sea level rise slowed down between 6,000 to 4,000 years ago, at which time the rocky open estuary that is known today as Los Peñasquitos Lagoon began to infill with sand from littoral drift, creating beaches. Unit 4, our open embayment facies, began to form during this time. The open embayment was established prior to 3,760 years ago and persisted in some capacity through at least 1,200 years ago. Here's a reconstruction of what we believe the lagoon looked like during that time. On the left, we have a cross-section view, and the right shows an aerial perspective. Light brown represents marine deposits or the open embayment. Dark brown are fluvial deposits, and yellow is immature marsh. Later on, we'll also see some green representing the mature marsh. On the aerial map, the circle represents the site for core 7, and the square represents the site for cores 3 and 4. So in the aerial view, we can see the creek channels with fringing immature marsh feeding into the embayment. The cross-section, meanwhile, illustrates that the embayment was completely open to wave action with no barrier. We see evidence of initial closure of the estuary starting at 3,760 years ago and indicated by increased mud content and decreased fine and coarse sand. The closure was likely initiated by sand that was transported down the coast, forming a low partial barrier across the entrance of the embayment. Up until about 2,750 years ago, the area was also populated with mangroves and pondweed, both of which indicate a wetter climate than what we see today. About 3,000 years ago, the vegetation in the embayment became more grassy. This is indicative of a shift to a drier climate, which is supported by other studies in the region. The drier climate may have facilitated further infilling of the estuary with sand, and as flushing events from heavy rain would have become less frequent, but we do not see explicit signals of drying conditions in our core data. So our first environmental transition occurred 1,200 years ago, as the open embayment of Unit 1 is overlain by the fluvial delta facies of Unit 2. Lining up almost directly with our fluvial delta facies, we see a short interval of wetter conditions that lasted from 1,200 to 1,050 years ago. This was identified by Kirby et al. In their work at Lake Elsinore. A significant influx of sediment would be expected after a wet period like this, which would explain the sudden creek channel migration and increased coarse sands. When extreme wetness follows a dry period, it creates the potential for increased fluvial sediment transport and geomorphic change. This means that the sediment load of the creeks would have been increased during this wet interval to the point where it could change the physical landscape of the area. Our only date for Unit 2 comes from a piece of unidentifiable plant matter near the boundary between Units 1 and 2. It is dated at 1,100 years ago, which is older than our youngest date from the shell hash layer. So keeping in mind that the sediment load would have been significantly increased during this time, we believe that it may have been a piece of older plant debris that was washed out from further inland and therefore not an accurate date relative to its depth. So we consider the shells to be more accurate. Here's another reconstruction where we see the fluvial delta in dark brown building out into the lagoon on both the cross section and the aerial map, and burying the shell hash layer in the process. It crosses over the site for core 7, but does not reach cores 3 and 4. So we also see that a sand barrier has developed, partially closing off the mouth of the estuary. From 1,220 years ago to 750 years ago, the world experienced what is known as the medieval climate anomaly. This event appears as a period of extended drought in the Southern California climate record, caused by a shift in the El Nino Southern Oscillation cycle to a La Nina-like regime. Unfortunately, I don't have time today to get into the nitty-gritty of the El Nino Southern Oscillation cycle, but the important thing that you need to know is that during La Nina periods, Southern California receives little rainfall and consequently decreased fluvial sedimentation. In addition to the effects of a La Nina-like regime, a shift to a warmer climate in general can cause a reduction in sediment supply, triggering a transgressive sequence in shoreline erosion. In the context of this study, that means something like a fluvial delta could begin to retreat landward. So we see the effects of this in the transition from Unit 2 to Unit 3 in Los Peñasquitos Lagoon. There is a sharp upward contact between the two units, likely representing a period of non-deposition or erosion caused by the climatic shift to a drier La Nina regime. This likely occurred partway through the medieval climate anomaly, but we do not have a precise age constraint. Here we reconstruct the infilling that occurred following the shift to a drier climate. We see the transgression in the transition from units 2 to 3 as the deltas migrate backward and the basin fills in with marsh deposits. The erosional surface of the delta, shown by this wiggly line, was overlain by immature marsh deposits as the delta was eroded and its sediment was likely redistributed into other areas of the lagoon. A tidal channel would have been preserved, though, providing a consistent flow of salt water into the new marsh. The sand barrier is also more developed by this time. Following the medieval climate anomaly was the Little Ice Age, which lasted from 600 to 150 years ago. We believe that this was the time at which Los Peñasquitos Lagoon transitioned from an immature marsh to a mature marsh. This was also a shift from the drier La Nina conditions to a wetter El Nino regime. The wetter climate could have facilitated increased sediment delivery to the lagoon again, and more sediment would build up an area of slightly higher elevation in the lagoon, allowing for more plants to colonize the area. Previous work just 200 miles north in the Santa Barbara Basin also revealed an increased pollen count during the early Little Ice Age, indicating that there was an overall shift to expanded vegetation along the Southern California coast at this time. So here we can see the mature marsh represented in green extending seaward out over the immature marsh of Unit 3. At this time, the mature marsh covers the sites for Core 7 as well as Cores 3 and 4. As the Little Ice Age ended, Southern California's modern arid climate took precedence about 150 years ago. This may be reflected in the return to immature marsh facies at the surface of Cores 3 and 4. Another contributing factor for the transition back into Unit 3 and the Central Marsh could be modern urbanization. By 1925, a road had been constructed across the tidal channel and a railroad was built through the center of the salt marsh. These developments are an example of habitat fragmentation. As a refresher, fragmentation is when a continuous habitat is broken apart into smaller segments. Continued development can cause the fragments to grow smaller and further apart from one another. The road across the mouth of the estuary has affected tidal flow, and the railroad across the center fragments the estuary into two pieces. Either of these developments could have triggered the return to immature marsh in the center of the lagoon, especially coupled with the drier climate conditions we see today. We have one final reconstruction figure bringing us up to present day. Here we can see that the mature marsh has retreated and only covers the site for Core 7, We also see the tidal channel restricted further by the sand barrier, which at this point has been altered by humans to support the road that cuts across the mouth. The main takeaway from this paleoenvironmental reconstruction is that we see 5 major environmental transitions over the last 4,000 years. 4 of these were triggered by climatic transitions, and the last was initiated by a combination of human activity and climate. There are a few general themes as well that crop up throughout the history of this lagoon. The first is that wetter conditions typically bring more fluvial sedimentation. Wet intervals have triggered 2 environmental changes within the history of the lagoon: the transition to a fluvial delta and the transition to a mature marsh. Both units 2 and 4 represent progradational sequences, meaning that sediment built out seaward. In contrast, dry periods trigger transgressive sequences, like the 2 shifts to immature marsh facies. A transgressive sequence means that the higher elevation environment retreats landward and can experience either non-deposition or erosion. Lastly, in the final transition from the mature marsh of Unit 4 to our modern day lagoon, we see that humans can have as great an impact on the progression of coastal wetland environments as natural climate conditions do. So now we get into the implications for restoration and conservation. So the initial motivation for this study was to understand the origin of the shell hash layer in core 7, which contained 2 whole Ostrea lurida shells, a species native solely to the west coast. These oysters once inhabited a much wider range of land from Alaska to Mexico. Now they're confined to sporadic assemblages, essentially between Canada and the southern border of California. The loss of suitable habitats for the species has largely been attributed to human activity in coastal environments, such as overfishing and urban development. Through this study, however, we have identified that their habitat loss in Los Peñasquitos Lagoon likely predated significant human alterations in the system and was instead due to an abrupt but natural sedimentological change triggered by a climatic shift to a warmer, wetter climate about 1,200 years ago. While this transition was natural, we do see evidence in our data that anthropogenic activity has more recently altered the ecosystem of the lagoon. This is shown in the return to immature marsh facies at the surface of cores 3 and 4. Over the last century, it has become increasingly difficult to differentiate between changes made by anthropogenic forces and changes made by climatic forces. It is well established that our climate is warming, but this time it is at a rapid pace and directly connected to human activity. While climatic shifts in the past may have been triggered by natural variability, future climate variability will largely be tied to human activities. Future restoration efforts for coastal wetland environments and Ostrea lurida habitats alike must take into account both natural climatic variability and anthropogenic influences to find success, as we see responses from both clearly reflected in the sedimentological record. All right. So to sum everything up, the primary goal of the study was to gain insight into the processes and events that can drive environmental transitions in a coastal lagoon in Southern California. We accomplished this by creating a detailed stratigraphic profiles of 3 sediment cores using grain size and total organic matter as paleoenvironmental indicators. We also investigated a shell hash layer to contextualize the presence of shells within the lagoon. We found that there were 4 environmental phases throughout the lagoon's history: an open embayment, a fluvial delta, an immature marsh, and a mature marsh. Each transition was driven by climatic changes, and the final transition in cores 3 and 4 was driven by anthropogenic activities in the surrounding area. So the bottom line, future restoration efforts must consider both natural climatic variability and anthropogenic influences to find success. So I'm going to be honest, I had an embarrassingly small number of pictures to put in here, so I just decided to use one field photo instead. First, I would like to express my deepest gratitude to my advisor, Joe Carlin, for his invaluable guidance throughout this project and for always encouraging me to make progress despite any challenges I faced along the way. As he explained, there were a few before. I would also like to sincerely thank the members of my committee, Nicole Benuso, for welcoming me to Cal State Fullerton and guiding me in the shell identification and taphonomic assessments. It's also Nicole's birthday today, so happy birthday and thank you for taking time out of your birthday for my defense. The other member of my committee is Matthew Kirby. Both my grain size analysis and loss on ignition were conducted in his lab. And during my first semester at Fullerton, he managed to turn a welcome to grad school course into one of the most engaging classes I've ever taken, and also taught me to be a better writer in the process. So thank you. I'd also like to thank Natalie Burston for her mentorship and guidance in helping me determine my career goals during my first couple years during this project. I could sit here and thank so many other people in the geology department, but I've already taken up nearly an hour of your time, so I'll just provide a blanket thanks to the entire geology department at Cal State Fullerton, including the folks who joined us in our field work to collect core from the lagoons, the lagoon. Lastly, I would like to thank my friends and family who supported me along the way. I expect to be continually celebrating this occasion as I get to see each and every one of you for the first time in over a year since the pandemic began. With that.